The first thing I do when doing this kind of problem is draw a picture. Okay, actually, the first thing I do is read the question. But from the question, I then try to draw a picture to see what's happening. All right, and when you read it, you hopefully notice you have 3 pins. All right, and you have this fence here that's already given. And so with your 400 feet, you want to make the most area you can. So what I do is I have to deal with a primary and secondary equation to solve this. You basically need to make an equation that you're trying to find a max or min of. In this situation, it's max. And sometimes you have to make a preliminary equation that goes into the important primary equation that you're dealing with. Okay, the preliminary is called a secondary equation, another equation to help you in the process. And here's what I mean by that. The secondary equation right here is perimeter, because we know the perimeter is 400 feet. And if you drew your picture, you notice I have 4 x's and 1 y should add up to 400. And what I do is I solve this for a variable. Here it looks like easy to solve for y, so I solve for y. And then if the question is asking for the maximum area, well, area is just x times y. That's simple, area. And so what I do is I take this secondary equation and I stick it in for y. And now what I have is a very pretty equation that I can take the derivatives of and find maxes and mins of with only x's, or one variable on the right side. You don't want 2 variables. It just makes a lot of problems when you're dealing with these kind of problems. So you want to make a primary equation that you're going to find a max or min of, and try to make secondary equations that plug in to make it all pretty and have as few variables as possible. Okay, so for this one, to find the maximum of this new equation that deals with the perimeter being 400, all right, I plugged it in, so this new equation. I first want to distribute, make my equation a little bit prettier. Then I take the derivative of this, because I'm trying to find a max. All right, and I'm actually going to take the second derivative. What's interesting is it's -8, which means this graph, this function, is always concave down, which kind of makes sense since it's a negative parabola. If you notice that, negative parabolas are always down, concave down. All right, so that kind of gives it away that whenever I find my critical number, it's actually going to be the relative max, because it's always concave down. Anyway, so what I now do is I set my first derivative equal to 0 to find critical numbers, because I'm trying to find a max. Critical numbers equal to 0. So I'm solving here, and when I solve this, I get 50. So x equals 50, we have a relative max for the second derivative test, because if I were to plug 50 back into this, which I can't, because it's always concave down, and if it's concave down, that means it would be a max if you think about concavity in a second derivative test. Second derivative test can be very useful, by the way, when you're dealing with these kind of problems, because it makes it kind of quick to find your verify it's actually a max. Okay. Now you could have done first derivative test just as easy. I just thought that was an easy derivative, and it's faster to do the second derivative test. Anyways, we now got to make sure we answer the question, because you know at 50 you have your maximum, but the question's asking for the maximum area. All right. So I need to now use 50 and find the actual area. So first thing I got to do is I got to put 50 into this original function here to find y. So if these are all 50, well, what's all that? When I plug in 50 to this function, I solve it, I get 200. So that's 200, and these are each 50. Okay, now it asks for the area, so now I got to plug it back into the area function, x times y. So 50 times 200, so I got 10,000 square feet. That's my maximum amount of area, given this scenario, given this amount of fencing, given this fence we're up against. Optimization problems like this, where you're optimizing or finding the maximum and minimum number, are very, very practical. Very interesting. Always helps to make an equation. Okay, a picture, sorry. And then from the picture, you want to make an equation that you're optimizing, but you might need to make a preliminary equation to help you. Okay, and then you take your derivatives and solve this equation you made to find relative maxes and mins. Now another thing you have to check out are endpoints sometimes. This problem doesn't need to worry about endpoints, but sometimes you have to worry about the domain. Like what if you got a negative answer, which wouldn't make much sense? Because when you're solving problems like this, sometimes you get numbers that don't make sense. So make sure you watch out for numbers that might not make sense, or check the domain of the scenario you're dealing with.